Now that we understand how to find the antiderivative of a function, where that function represents a rate of change, that gets us back to the original value of the function, which if you're taking the antiderivative of f prime, your answer would be your beginning f of x function that we would have found the derivative of back in previous chapters. We know how to integrate. We know the rules of integration now that we learned about in 5.1 and 5.2. In this next section, you're going to see how it comes together in a lot of different application senses. So this is going to be called the definite integral. The definite integral is where you no longer have a family of functions as your answer. We're not going to have that plus c constant this time. We're going to be given an actual value for your answer. And the definite integral is related to the fundamental theorem of calculus. You're going to see how it comes together. First, here's the concept. You've got a function, and in the graphs that you see on your notes paper, they're sketched in pink. It's that wavy line. We want to find the area between the two functions if you had a separate function below it or above it, f and g, let's say. Or in this case, for this section, we want to find the area between that function and the x-axis. And that's the idea we're going to be working on for the rest of this week. We see the sketch on the left that shows you all of that area that's been shaded in light blue for you. That's the region of area we want to calculate. Now, the two graphs that you see to the right of that show you how this can be done. The first graph, which is in the middle right here, this is where we've divided up our region underneath that f of x curve into rectangles. Each of the rectangles have the same width, so I want you to recognize that each rectangle has the same width. Okay, so that's important to note. And so in this graph, the one that I just wrote above, we have 6 rectangles. In other words, we have 6 sub-intervals. I took the entire interval from A to B, and I split it into 6 equal divisions, okay? And then I've constructed 6 rectangles. The height of each rectangle is based on the function value at a particular point. Notice that each of the rectangles has the top left corner that hits my function. The top left corner of each rectangle hits my function. And so the top left corner of my rectangle tells you the height of that particular rectangle. That'll be important shortly. Now the graph to its right, again, is the same exact quantity of area that's been shaded underneath this graph f of x from A to B. But now instead of having 6 subintervals, I have 24. And you can probably see that these 6 subintervals gives you an estimation for the actual area that is a little bit off. We didn't calculate this piece here. We didn't calculate this piece here. We have too much here and we have too much here. And so it gives you an estimate, right? And the graph that's to the further right, all the way to the right, does a better job. We have less area that we're not including underneath that curve, and we have less that we over included. And so it's going to balance out to a closer estimate of the actual area that we really wanted to find. That's the actual area, and these two pictures give estimates. So this is the first concept in this section, is dividing up this region of area into rectangles. Now, why are we using rectangles? Well, we know how to find the area of a rectangle. We know the area of a rectangle is base times height. It's a geometric figure. Had this function been a straight line, I probably would have either used a triangle or maybe even a rectangle in that case. But it's not a straight line, it's a curvy function. And so the best I can do is split this into rectangles. I lost my picture. I apologize. Another approach that theoretical calculus students will examine is splitting this area into trapezoids. Trapezoids do an even better job of estimating this area. We're not going to do that. We're going to focus on rectangles because they use trapezoids because that is another geometric shape that we do have a formula for the area. Okay, so you compare the two pictures on the right, one with the 6 subintervals and one with the 24 subintervals, and you can see that the 24 subintervals did a much better job of representing that area as an approximation. And so the more subintervals that we use, or the more rectangles that we use, the better the estimate of the actual area. So that's what this line is telling you. Okay, that's a pretty obvious fact. The more rectangles we're able to construct, the better the area is going to be. Now, it's also going to create more work for us. I'd rather find the area of 6 rectangles rather than 24. I don't know about you, but 24 does give you a better answer. What the idea says is you divide the interval from A to B into a given number of intervals. And so you'll be told that in your problems. Like, take this interval from 1 to 10 and split it into 4 subintervals or 8 subintervals. And that tells you how many intervals or how many rectangles you're going to be making. Now, the width of each rectangle, the width is found by taking the entire distance from A to B and then dividing it by n, right? So the distance from A to B is found by subtracting. All right, we use b minus a because that gives you a positive number. And you divide by n. N is going to be how many subintervals you're told to use. Now, this is going to give you delta x, or the change in x, or the width of each rectangle. Right? So that's going to be the same all the way across. Each rectangle has that width. You know A and you know B, and you'll be given n, and you can find that width of each rectangle. Now let's talk about the heights of the rectangles. As I mentioned before, each corner, each top left corner of my rectangles hits my function. Here it is again. Okay, and so the top left corner of my rectangles are hitting my function, and that determines the height of that rectangle. And in that case, I am said to use the left side of the rectangle for my endpoint. Okay, and so that would be this particular value of x. Now, the reason I need to know this is because plugging in this value of x, whatever it happens to be, here it's in general of just x1, plugging in that x1 value into your function gives you the height. And so in other words, the height of the first rectangle is going to be f of x1. Okay, the height of the second rectangle is f of x2. The height of the third rectangle, if it were drawn, would be f of x3, and it would look like this. And so on and so forth. All right, now why the left? Why the left? Well, you're going to be told, next, you're going to be told that you could have used the right endpoint, or you could have used the midpoint, right? So I could have used the midpoint and gone up to hit this graph, and then constructed a rectangle as so, and the height of that rectangle is going to be f of whatever that midpoint number is, okay? And so the process is irrelevant. You'll be told which process to utilize, whether it's left or right. I don't believe we're going to deal with any midpoint problems in this class, but it could have been done. But that's telling you the height, okay? Could have used left, could have used right, could use the midpoint, doesn't matter. The sum of all the areas of all the rectangles gives you an approximation to the actual area under the curve. So once again, you're finding the areas of each rectangle, and then you add them all up, and that's going to give you the approximate area under that curve. Close enough. The more rectangles or subintervals we have, the better, the smaller the width is going to be of the rectangles, and so as the widths become smaller, the approximation becomes better and better. So I'm trying to highlight this without overpowering the ink on my device here. Okay, so the more rectangles or the more subintervals we have, the smaller the widths are going to be, and as the widths become smaller and smaller, the better the approximation of the area. All right, we want those widths. This is what the main idea is. The widths become smaller and smaller, the better the approximation of the area. And you see that in the picture above with the 24 rectangles versus the 6. 24 rectangles had a very, very small width, but it's going to overall give you a better answer. Next comes the Riemann sum. The Riemann sum, you may have heard of it if you had a pre-calc class before or an AP calc class in your past. The Riemann sum is where you take the limit of all of the areas as the widths become smaller and smaller, right? So we want the widths of the rectangles to become as small as possible. Now, consequently, if those widths become smaller and smaller, the number of rectangles we have becomes bigger and bigger, okay? The width of the rectangle gets smaller and smaller, as in this graph right here for 24. As a consequence, the number of rectangles becomes increasingly bigger. And so that's the number of subintervals becomes increasingly bigger. Now, the Riemann sum is called A. And A is where you take the limit of the sum of all of those areas. And so we write that as the first height plus the second height plus all the other heights plus the last height all together, take that times the width at the end, and that's going to give you the total area. And if you do some quick math here, this would be the limit as the number of intervals gets big. Here's the first rectangle's area. Here's the second rectangle area. Here's the third rectangle's area, right? Because it's the height times the width. It's the height times the width. It's the height times the width. And you're taking in the sum of all of those areas. The number of terms you're going to be adding together is going to get larger and larger and larger because I'm letting the number of subintervals get bigger and bigger. Now, as we take that limit, as we increase the number of subintervals, what we get is this approximation to the area under the curve, and that area answer is called the Riemann sum. That's the Riemann sum. And we've identified xj to be the left endpoint of the jth rectangle. All right, so before we do a couple of examples, I think we'll take a break. So think about what we've just discussed. Maybe become familiar with that Riemann sum formula. We're going to be using this now in the examples that follow.